Welcome back, everybody. Day 5. Before we start with the math program, just a quick announcement. So I was told to say that the certificate of attendance of the conference will be available on the website of the conference after today, when the conference is done. So you can download it, print your, it's just one PDF file. You can download it, print your page in case you need it for university, so on. Okay, then let's get started with the last lecture of the first mini course. So, Kris, Combinatorial Geometry in Hodge Theory.
Thanks, Martha, and thanks for coming back. I know some people were in Lapa last night, so I won't say names since we're on video. But so I want to, in my last lecture, as I kind of promised, at least in the summary, to say something about tropical algebraic cycles and this Hodge conjecture, tropical Hodge conjecture. I do want to start, though, with a couple of corollaries from last time, just to, for one hand, to try to justify this definition of cohomologically tropical and wunderschön and things that we had. So this is basically a generalized IKMZ theorem, which says that, so remember, this was a theorem that told us that in cases of nice tropicalizations, locally matroidal tropicalizations, the tropical Betti numbers, the tropical dimensions of HPQ, were giving us Hodge numbers, or even more so, information about the mixed Hodge, the limit mixed Hodge structure of the family. So we can actually change this up to being now, so look very similar. So let me put algebraic here because I will want to take a semi-stable completion of projective varieties. So when I say projective, I mean I want a family of varieties in projective space over this disk with semi-stable completion, so to the whole disk, meaning that we'll have some special fiber x0. Okay? And this x0, or let me say the condition, so that's the setup, and the condition is if now instead this tropicalization, so remember before we said it had to be locally matroidal, and this was very strong, and this actually gave us information about what the pieces of the tropicalization of the variety would look like. But now all we need is that this is a tropical homology manifold. So this means that this polyhedral complex, this combinatorial thing, satisfies some duality theorem for homology theory everywhere. So everywhere it has tropical Poincare duality. And so that was the kind of combinatorial condition. And we want also all strata, all open strata of this special fiber, right? So this is some reducible variety with tons of components. Those components intersect. They give us all these strata. We want to take the open strata. If these are all wunderschön, then we can conclude basically the same thing as the IKMZ theorem. So I won't write it out in full details, but these are isomorphic to the associated gradients of the weight filtration of the mixed Hodge structure, limit mixed Hodge structure on this whole family. So numerically, so this is saying that these this was with Q coefficients, that these vector spaces have kind of more information about the family. Numerically, just that the dimensions of these vector spaces over Q give us Hodge numbers of a generic member. So T is a point in the punctured disk. Okay, so we can loosen the locally matroidal, loosen the condition that our degeneration basically looks like a bunch of linear spaces or complements of hyperplane arrangements, to being something more general. And so this was not just the fact that we had this definition of cohomologically tropical, which was way stronger than just asking for FPs to recover the cohomology of a very affine variety, right? This was something asking for all the strata to have their cohomology be known. It wasn't just because we could prove a theorem, but it's also because we could generalize this theorem. Okay. The second thing I wanted to...
Sorry.
Yeah.
Explain why this is a generalization or a strengthening of Hodge.
So why does it specialize to the one we had before, or why? Yeah, so I said last time that matroidal things, matroidal fans satisfy tropical Poincare duality. So anything that's locally matroidal will be a tropical homology manifold. And remember, this Wunderschön definition was in terms of the mixed Hodge structure on this open variety, on the strata of the open variety, that it had to be pure, of the right type. And it turns out it was known long before any of this. The result of Shapiro is that the mixed Hodge structure on a complement of a hyperplane arrangement is of that type, has a Hodge structure of that type. Yeah?
So I guess I'm slightly confused as to what tropicalization is now codifying. Because this result tells us that sort of the cohomology of the tropicalization gives us Hodge numbers of the fibers.
Yes.
So is there some information about the degeneration itself, or like the family itself? Or?
Both.
Yeah.
So numerically, it's about a fiber. Mm-hmm. Okay?
But the mixed Hodge structure.
But the mixed Hodge structure is of the family.
Okay.
Okay. So here's a second kind of more maybe easily digestible corollary, and more obviously provable corollary from last time, what we did last time. And this will lead us into kind of what people call the Hodge theory of matroids, or combinatorial Hodge theory in the sense of June He. So if X, so remember now this is just a single X in the torus, is cohomologically tropical, and we have usual X, it's a tropicalization. Sigma is going to be any unimodular fan with its support being equal to the tropicalization. Right, so there's a choice there. And I want to take this also to be, let me take this to be a quasi-projective fan. So if you don't know what that means for a fan, there's a toric variety associated to the fan. We want that toric variety to be quasi-projective. Okay, so it means that there's some completion of this thing to a projective variety. If you want, this is a subfan of a dual fan of a polytope, of a lattice polytope. Okay. Then remember, we defined the compactification of this X with respect to the fan. And we saw also, well, in certain cases that or in every case, that HPP of this compactification was the Chow AP of the Chow ring. Of the fan sigma. But when we're cohomologically tropical, everything off the diagonal will vanish. So this will actually also be equal to and also everything here is with Q coefficients. I should be more careful because I will switch coefficients today. So these two rings are isomorphic. There's nothing off the diagonal in this, and it turns out that they satisfy this so-called Hodge package. So I don't actually know why it's called the Hodge package, because there's many names of people who appear in the properties for the Hodge package. So the first one is that it has Poincare duality, this ring. So what does that then mean? It means, let me just write shorthand A and AK for these. Means that there's a nice perfect pairing between the complementary graded pieces. So this first multiplies to give you something in AD, but we have a degree map to Q, and this pairing is perfect. For all K. Okay, so this is a Poincare duality from the perspective of this Chow ring. We saw a different version of Poincare duality for the tropical homology that was kind of more flexible, because I didn't need this to be compact, and I could do this with Borel more stuff. But okay. Oh, I was hoping to fit everything on this one board, but we'll see. We also have a hard-Lefschetz theorem. So for this, we need to have a certain notion of special classes in A1. And L has to be so-called ample. Okay, it's not too difficult to describe what this ample condition means, but let's not worry about it for now. It has to do with some sort of convexity of a function on the fan defined by L. Then, of course, we can multiply by this class L as many times to bump up the degree. This is an A1. And if we multiply this many times, then we go from AK to AD minus K. Okay? And that this is an isomorphism. Right, so the Poincare duality tells us that these two have the same dimension, because you have a perfect pairing between them. This is actually giving us an isomorphism, multiplying by the class L. Okay? And the last one of these so-called famous Hodge-Riemann bilinear relations that are responsible for all kinds of log concavity results in sort of Junhe and many co-authors program, that we can define then a intersection pairing on AK with itself by using this ample. So L will always be ample, still down here. So K will be smaller than half D. And so what we can do is we can take, say, this factor and multiply it by L enough times to get up to here and apply the intersection form. And we'll do that with a sign so that, this is the definition then of this on AB. It's minus 1 to the K. Yeah. Times, so here we have the degree map, which takes us from AD to back to Q. So the degree of when you take L, D minus 2K of A times B. Okay, so that's a perfectly good form, quadratic form on A to the K. And the claim is that it's positive definite on the kernel of the things that vanish when I do L one more time to them. On the kernel of L D minus 2K plus 1. Okay, so we know the signature of this intersection form, essentially. And knowing the signature of this intersection form is something that allows you, at least on, so this is called the primitive part, the cohomology, the kernel of doing this map one more time, right? This is an isomorphism, but if I do it once more, you end up picking up something in the kernel. Okay? So why is this theorem true? in this case. So we have, I mean, I'm using this theorem to introduce all of these properties that maybe some people have already seen before. But in the context of yesterday's talk, why is these properties, why do they hold? Remember that when we were cohomologically tropical, we had the isomorphism with the cohomology of this x bar. Okay. And this, when I have the assumption that this is quasi-projective, okay, this ends up being a non-singular projective variety over C, and its cohomology, with only cohomology in the algebraic part, its cohomology ring will satisfy these properties. Okay, so this is a Hodge package. Let me put June's name next to this because, well, I think the most interesting application, or this naming of it as a Hodge package, came up in the context of the Chow rings of matroids. So some matroids are included in this theorem, right? The ones that are representable over C. But there's something that's sort of larger in this theorem than was proved in the first kind of Hodge theory for matroids paper of Adiprosito and Katz. I should put Adiprosito and Katz. This was the first naming of this for Hodge theory of matroids. Where they proved that the Chow ring of the matroid fan, where I put sigma m here, satisfies these properties. Okay? But this theorem also allows us to take any other fan structure on that sigma m. If you have the support of a matroid fan, and that matroid fan is realizable over C, you have all of these properties. You have a different ring, a different intersection ring, but you have the same properties. Yeah. All right. Okay, sorry, Kähler package. Hodge theory for matroids or Kähler package. I don't know how you choose whose name to attribute these three properties to, because as you see, there's Poincaré, there's Lefschetz, and there's Hodge and Riemann. This does hold for Kähler varieties, so that's maybe why you could put the Kähler, okay? But these are just artifacts of the cohomology ring of a non-singular projective variety. And in the general world of, say, fans, which are not complete, you should not expect to have these properties. So an incomplete fan is not a projective variety. It might be quasi-projective, but you shouldn't expect these. Yeah? There was another question? Yeah?
So this is for any fan with a support,
Yeah.
a realizable
Sure, a matroid, but also even more general. So matroids are, linear spaces are cohomologically tropical. So this works for matroids that are representable over C. But
the support of what would be an example of something that is like this, but it's not the support of a matrix?
what are some examples of this? What are some examples of cohomologically tropical varieties? So I don't have a full classification of them, but we do have other examples. Right? I should have put those in my talk yesterday, but I ran out of time. So I think if I try to give more examples now. So we know what they are in dimension 1. That's very easy. We don't have a full classification in dimension 2, but we do have other examples that are not complements of hyperplane arrangements. Okay? But just using this corollary to give us some continuity from yesterday and show that this gives you a way of proving for many, many varieties, or many, many fans, sorry, anyone, not just the matroid fans with the one fan structure that I showed you, but any fan structure, you're going to get this package. Yeah?
But the AK fan of the non-realizable matroid satisfies this condition.
But it doesn't satisfy this condition.
Yeah.
Yeah. No, so this does not cover non-realizable, but it covers very many fan structures on anything that's realizable.
But it is true also for the non-realizable.
So let me jump to now. So this was algebraic geometry. Let's give a combinatorial generalization, right? So we already know, many people in this room already know one combinatorial generalization, and that is if I put an M here. Okay, but that's a specific fan structure. So what I want to at least advertise, because I think some people who know this story maybe don't know this nice generalization. So I want to put kind of many names here. Also Ardila, Denim, and then kind of the important, the generalization that I want to write down here, that's for any fan structure, comes from Amini and Picares. Okay, so let sigma be any unimodular fan structure on the support of some matroid fan. So remember, this was a distinguished fan structure, but you can take its support and put a different fan structure on it. And if it's unimodular, then, well, this Chow ring ends up still being isomorphic to the compactification of the support with this fan structure. I can take the tropical cohomology if I want. So this is just an aside. This is saying that there's still nothing off the diagonal in these groups. That you shouldn't expect for a general fan either. We said last time these are sort of like the Hodge spaces for fans of Brion, and he didn't know what the HPQs for P not equal to Q were when they didn't vanish. There were some results where you know when they vanish. This also satisfies the Kähler package. Okay, so the first authors prove this for sigma m. The second group of authors proved it for, well, let's say the conormal fan, which actually is a different fan structure on special matroid fans. A product of a matroid fan with its dual is actually still a matroid fan, and they gave a different fan structure on it. There's also there's many names here for special cases. There's the augmented Chow ring, which is a Chow ring of a different one. And what Amini and Picares, an artifact of their work, is that the Hodge package, the Kähler package, is sort of preserved under fan subdivisions, by bistellar subdivisions of fans. And there's a weak factorization theorem that tells you can go from any unimodular fan on a given support to any other unimodular fan on the same support by doing lots of different bistellar subdivisions and their inverses. And they prove that those operations don't change these, or maintain these three properties. You certainly change the ring, but you don't lose the properties.
So here, quasi-projectivity is not linear.
We should have quasi-projective if we want something in the ample. Thank you. Otherwise, these are very interesting. Okay. Amini and Picares also show that, okay, so this subdivision argument has nothing to do with the artifact of the matroid fan. If you start with a fan that you know satisfies it, you take its support, you take another fan structure, it still works. So Kähler package is preserved. So preserved, the Chow ring is not preserved, but the properties of the ring are preserved. Under subdivisions, again, we should subdivide in a way. So. And there are inverses then. Taking products of supports. And I'm going to write something here with a star because to explain the conditions for what you need on this operation in order to preserve it. Well, one, I'm not going to explain what the operation is. You can read about it if you like. And I'm not going to explain what the conditions are because I don't explain the ingredients to the operation. So it's hard to tell you what the conditions are. So let me just put tropical modifications, but with a strong star here. You're only allowed to do them of certain types. Okay, but I think that there really are other operations that this is preserved on that are also kind of more akin to different kinds of birational So we should think that these bicellular subdivisions on the level of the torque variety, these are birational operations. These are blow-ups, subdividing. But they're blowing up on the kind of toric on the boundary divisor, on this SNC divisor that is the complement of your big open part and the boundary of the divisor. And I think there are other operations that you can put here, and I think we're still far from a full classification of which fans satisfy these properties. Yeah?
If I remember right, I mean, there is they use Lorentz polynomials as a proof, but I was wondering, in this proof of Brent and Ase, as you said, with Lorentz polynomial is also a Shokrieh, but it's a scalar bracket in the
So
magic.
I did want to say one thing to lead, because we've heard a lot about Lorentz and polynomials and how they're useful for proving log concavity results. So the way that you get log concavity results out of the scalar package is from the third one. It's from Hodge-Riemann. Okay? But it turns out that this scalar package is kind of overkill. If you want to prove, these kind of Alexander-Frenchel inequalities and then hence get some log concavity results out of it, you don't need all of this, even from the fan perspective. So that's, I think, the whole idea of Peter and June to come up with Lorentzian polynomials. It's kind of checking all of this and checking something kind of more just on a polynomial level. There's also this, if you just want log concavity results and you want to do it via intersection theory on fans, there's a definition of Lorentzian, called Lorentzian fans of Test and Ross, which are much weaker. So these are fans. I'm not going to write down what they are. They're fans whose intersection theory. So this is the intersection theory, that you have some quadratic forms here. Okay. Gives Alexander-Frenchel inequalities, aka log concavity results. Or not aka, but implies some log concavity results. And the properties to be a Lorentzian fan are very strictly weaker. It's much easier to satisfy. And Dustin Ross also shows that it comes down to checking a condition on the two-dimensional star fans. To get all of these properties, that's not going to suffice. This is much stronger. So I think that, as we heard in Frederico's talk, you might be a combinatorialist very, very interested in log concavity. That's great. If you're not, then the selling point of this of the log concavity results is that it produced all of this interesting mathematics. These unexpected results even say, let's say about Chow rings of toric varieties, right? Like this is actually an algebraic geometric object. It's not a complete toric variety. Why on earth does it satisfy these properties? Yeah.
I think I missed something. This second is for this corollary of the first one?
No. Sorry, this is a corollary of last time. Thank you. These are two corollaries from yesterday. In a different sense. One is still in the local case, this one. And this one is taking some kind of the local things that we did last time and making it something global.
So is every scalar trivial fan in the sense that Lorentzian?
Yes, I think so. Yes. Yes. Okay. So, yeah.
So the ample comes from
I can't hear you.
the ample comes from a projectization, this LL.
Does it come from a projectivization? Well, okay. The ampleness, you can describe it purely in terms of like a PL function that something in A1 defines on your fan. Right? So this is a sum of monomials corresponding to rays, and you can take their coefficients and define for yourself a function, PL function on the fan, and you ask that function be strongly convex. But this kind of quasi-projectiveness is hanging around so that we actually get such
For the
functions.
existence.
Yeah. Okay. So remember last time we also had we had this Hodge isomorphism in general. Okay, so what I want us to do is think about when we don't have this isomorphism, so when there are things off the diagonal, I want to try to encourage us to think about this being the algebraic cycles, okay, and this being more topological cycles, this being giving us the Hodge decomposition. Even though we know from our theorems that even in the realizable case that's not exactly true because, oh, I just erased it. These are graded pieces of a mixed Hodge structure of the limiting mixed Hodge structure. Okay, but we can still ask ourselves, for HPQ, instead of having A star here, which of these properties, or how does this Kähler package or does it make sense, generalize to the HPQs, no trop here, just HPQs. Okay. And well, in the fan case, we know that HPP, the sum of them is this AQ. So the fan case is no longer very interesting to us. Sort of falls in line to whenever this corresponding ring has the Hodge or the Kähler package. But when X is the support, or X is a tropical variety, actually, of P, a more general polyhedral complex. Okay, so we've seen only a few examples of this. We saw like X could be a tropical hypersurface. Okay, and we will want to take compact things. We should have learned our lesson in the case of fans. So we'll think of some compactifications here. We also had tropical linear spaces in Alex's talk, and well, Matroid subdivisions. And maybe we want to compactify these somehow in order to be looking at something that has a chance of modeling something projective. And many, many other examples. Okay, so do we have elements of this Poincare duality, Hard-Lefschetz, and Hodge-Riemann for our tropical homology groups in these more general settings? And we do if we impose a whole bunch of conditions. Yeah?
So for me, like the third and a half part of the Kähler package is something like sad reality or like the hot stars.
Okay, yeah. We're not at that state of the art yet. Very good. So of course, now that we have these PQs, right? Well, okay. We'll say some things. It depends in what generality you mean Serre duality. I might give you something that you'll be happy enough with. Okay, so this is again in a kind of, most of this is in a, I'll write the attributions as I write the properties down. This is one setting, which riffs on the whole Matroid scenario again, where we can collect a whole bunch of properties of this, this total ring, so the sum of all of these together. So we need to make some constraints. So let's let x will be a compact. Okay. Let me say it like this. X0 in Rn, this is going to be a tropical variety. So that means that it's a support of a polyhedral complex. It has weights, rational polyhedral complex, with a weight function everywhere equal to 1. And we want it to be locally matroidal. So that means every star fan, every kind of strata of this space, if I zoom in and look at just what's happening around it, it's going to be at the support of a matroid fan up to some GLNZ. I don't really care changing coordinates. Okay? And I'm going to need also this weird fact for many of the results. I want all of the vertices to be rational coordinates. Okay? I'm going to put this in brackets because not everything needs this. All vertices in X0. So that means I'm abusing notation. There's some polyhedral structure on this X0, and I'm only thinking about the vertices. Okay. We're going to take X, be the compactification the cubical compactification. Given by the fan, which is the recession fan of X. Okay, so take all the unbounded directions in X. There's going to be a bunch of them. Take their collection. It may not be a fan. Put a fan structure on it if it's not. Okay, and I need this to be quasi-projective. Again, because to talk about hard Lefschetz and stuff, we need some ample classes. Okay, so this is the caveat star, and I'll add it when I need it. Oh, X bar is the, no, X. That's X0. Okay, then we have Poincaré duality. Just a second. Yeah. So Poincaré duality is going to be a pairing between complementary graded pieces. And again, this is going to map to X. HDD of X, but then we can fix a degree map and we get to Q. This also works over Z, actually, but let me just use Q coefficients everywhere. Now we need the condition. So this was first done with R coefficients by Yel, Smaka, and myself, and then with integral coefficients. So I put it here with Q coefficients, but integral is definitely stronger. Also with Rao and Yel. Hard Lefschetz looks almost exactly the same, except we're bigraded. So L, we have to have a notion of ample class, which I won't describe. But now we hit it with D minus P minus Q times. The D is dimension of X. So that this is an isomorphism. Okay. There was another thing we knew when these were actually, the dimensions were giving us Hodge numbers of a complex projective variety, And that was that if I take HPQ, it should be the same dimension at least as HPQ, as each QP. So in the Hodge decomposition, these are actually complex conjugated vector spaces. Oh, and I should say, this is due to Amini and Piquerez. There's another property also where I require this Q assumption. And that's going to give us a map, an isomorphism between HPQ and HQP. Okay? So if we think about, okay, let me draw out a kind of tropical Hodge diamond here. Okay? Poincare duality is a kind of reflection in the center of this diagram. So reflection through the center, so you can go through the center. HL is just going up 1P and up 1Q. Okay? This, and then we do that enough times to get up to the kind of corresponding reflective spot. So. What am I doing here? H21, H12, H22. This is in D equals 2. This weight monodromy, so this is going to give us a isomorphism between these two. So that's like going from here to here. All right, so Lefschetz is going like this. If we want to get from here to here, there's actually a map that here decreases P and increases Q. And we need to do that Q minus 1 times. So there's some map W. This map's very important for the tropical Hodge conjecture, which I'm going to get to hopefully very soon, that this is an isomorphism. This is, again, Amini and Piquerez. And this map is the so-called eigenwave map. Of Mikalkin and Zarkov. So when we're in the kind of realizable setting here, when this thing comes to us as a tropicalization of a family, and it's locally matroidal, we have a limit mixed Hodge structure on the family, and this eigenwave map is actually giving us the monodromy operator on the limit mixed Hodge structure of that family. Okay? But they have a combinatorial description for it, and so you can describe it for any x. You don't have to come from algebraic geometry. Here's where I needed to be very careful with the coefficients. In this case, with this assumption star, I can put Q and Q here. And since I'm running a little bit short on time, I'm going to not write out the full Hodge-Riemann, but I'm going to say that there are Hodge-Riemann and give an example. So there is a form that we can define. I'm being very fast here. To Q. So there exists a form for all P and Q on that vector space itself. And it is positive definite on some subspace called the primitive part. And normally the primitive part, we use the Lefschetz class to define the primitive part. Here we have to use both W and L to define the primitive part. I'm not going to give the full definition, but let me just say example. if x is dimension 2, okay, then this signature on h11 of x is 1 plus the second Betti number of x, so whatever the second Betti number of this two-dimensional thing is. And then, so that's how many positive eigenvalues you have. And this is how many negative eigenvalues you have. Okay, so if you know the Hodge index theorem for surfaces, it says that the signature on H11 of a complex projective surface is 1 comma the rest. Okay, so this should be telling you that if you weren't already convinced that these aren't the same as the Hodge, these groups aren't the same as the Hodge decomposition of a complex projective variety, now we know that the intersection forms that they carry, even though they have intersection forms, even though they have Leschetz, even though they have all this stuff, it's not the same. Okay? But if we restrict to so-called algebraic cycles, so these are one-dimensional tropical varieties, so tropical curves in X, and generalizations where I allow negative weights, possibly, then the signature is 1 comma, whatever the dimension of the algebraic cycles are, minus 1. Okay.
So in the definition of Lorentzian fan, there are AF inequalities with respect to cycles, not cohomology.
I can't hear you. Sorry.
In the definition of Lorentzian fan there,
Yeah?
AF inequality is with respect to algebraic thought, is with respect to the theorem, not.
Yes. So this was all for the, sorry. Yeah. Whose intersection theory in here?
Yeah, not the cohomology.
No. I don't know what the cohomology, tropical cohomology of a Lorentzian fan is. Yeah. So what do I mean by these algebraic cycles? And this is really the kind of the tropical Hodge conjecture that I'm trying to get at. So allow algebraic cycles in H11 of X. Okay. So I've got officially 1 minute left. But recall that last time when we had this weighted polyhedral complex. Okay, so this was a tropical cycle. We defined, so of dimension, okay? I defined some sort of fundamental chain in HKK, and I defined it in HKK of Y, but it's not so hard to say, I take a subdivision of X, and I can define this in HKK of X. This would have Z coefficients. Okay. And if we want, then we have Poincare duality here. So I wrote Poincare duality as a pairing on cohomology, but this cohomology is actually dual to the homology, so I actually get an isomorphism. And this is actually Poincare duality over Z, which I said holds, I didn't actually state it. Okay, so we're thinking about what is the image of I take all the tropical cycles, these actually form a group, and I think about what they do here. Okay? So the tropical Hodge conjecture of McElkin and Sarkov states that, or so the conjecture is that the image, let me call this map that goes from algebraic cycles to the cohomology. Let's call this psych for a cycle class map. That the image of the cycle class map is equal to the kernel of this W map. This one here. Okay? So I haven't given you the definition of W, but it turns out that one inclusion is very clear. That if you're coming from an algebraic cycle, you're definitely going to be killed by this cycle class map. Okay. So then, okay. There's one subtlety here. So this Y lands in something with Z coefficients. Okay. The W map on the cohomology, if I do it just once, so let me get this right, it's going to decrease the first index and increase the second index. But what's kind of wild, or what makes this conjecture sort of difficult, is that this map doesn't preserve coefficients. So however you define this map, you can only really ever guarantee that it's going to take values with real coefficients. And this is the subtlety of this Q assumption. If you have this Q assumption, then the W can go from Q coefficients to Q coefficients. And if you drop that assumption, you can't even take Q coefficients to Q coefficients. You have to go to R. And we can do Z also to R. So this is where the kind of transcendental nature of the Hodge conjecture comes in the combinatorial version. Right? If we were thinking about Q and Q here, R and R here, then we have vector spaces, and you're looking at the kernel of a linear map. I mean, okay, you can at least easily describe it. Once you have this going on, it's even hard to describe what the kernel is. So I just want to say very shortly that we've managed to, if I can have a couple of minutes? Okay. Two scenarios where this Hodge conjecture has been proven, kind of in general, not just in examples. So the conjecture is true for k equals 1, 1. So this is the Lefschetz 1, 1 theorem, but in a tropical. So k equals 1. This is the Lefschetz 1, 1 theorem in complex geometry. This is true. And it even works with Z coefficients in complex geometry. And there's a tropical version. So this is Yel, Rao, and myself. And if we bring back the assumption star, so meaning that the vertices of this complex were defined over Q, and what that gives us is that this map, the W, is defined over Q. So in the sense, it's taking out any kind of transcendental nature or any kind of mixing of coefficients. And this is Amini and Piquerez. Conjecture interesting. And this is a proposition of Concavity. In so-called, so four-dimensional tropical abelian varieties of so-called Weil type. All right, so these are, we learned from Farbod's lecture, a tropical abelian variety is you take R to the G and you quotient by some lattice. So this is take R4, quotient by some lattice, and you take a special kind of lattice so that the resulting real torus and corresponding the complex one that maybe tropicalizes to it has an extra symmetry. It's very, very explicit. If you look up a note of Zarkov, he explains this proposition of disproving the Hodge conjecture using tropical geometry of Concavity. It turns out that in this case, there are extra classes in the kernel of W, and the challenge is to show that they can't be cooked up with tropical cycles. So you can take a look at this note, and it's very, very explicit. I want to just draw a picture of this 1-1 theorem in the abelian variety case, abelian surface case. So in the abelian surface case, we're quotienting R2, and there's the honest integer lattice in R2. And then to get an abelian surface, we want to quotient by some other lattice. So our lattice that we quotient by is maybe generated by some W1, W2. Okay? And it turns out that H11, put it in the lower side so we see it in homology, is isomorphic to, well, it's generated by a class of the torus times an integer vector, and another class of the torus times some integer vector. So this has actually got a very explicit description, as it's H1 of this torus with coefficients in Z squared. Very easy. And if something in the kernel would just, I didn't give you the description of this map, but it turns out that in order to, if you have something in the kernel, it would be something like this cycle with an integer vector on it. This is an integer vector, coefficient in Z2. This cycle with an integer vector on it. And in order for it to be in the cycle, it's the exact same thing as saying drawing the lines from W1 in parallel here, from W2 parallel here, and from the origin parallel to their sum, that those are concurrent. So it turns out that the tropical cycle that's equal to the class alpha in homology is this curve that you've drawn here. And this is just a very classical theorem known as Chev's theorem of when three lines drawn from vertices of triangles end up being concurrent. And this is just the Lefschetz, this ends up being the Lefschetz 1-1 theorem for a tropical abelian surface. So I wonder if in this case, if you can do the, I don't know, whatever the analog in 4 dimensions of Chev's theorem is for 2-dimensional things, you might actually find cycles that give you classes in this kernel, and I mean, maybe this proposition of Concavity doesn't work if that's the case, or maybe it does. So that's it. Thanks sorry for going over time.